All right, so we are physically moving from one topic to another. We're moving from statics to dynamics. And the essence of this, well, I don't know that we necessarily need to recap it too much, but we can do, just to say that the two last things we talked about were accelerating fluids, which I kind of alluded to as kind of oxymoronic. And that is that if you take a fluid that is sitting in a pail and you get rid of that fluid and accelerate it by some amount in the y direction, as we called it, and or the x direction, sorry, z direction, then you get a slope of the fluid. And we can determine what that fluid slope is by doing what we did last time. We just put the pressure here is equal to dP equals 0. Some people asked at the end of the last period, why do we say it's equal to 0? Because it's atmospheric all the way along here. And so the pressure doesn't change as we go along here. And as we did that, we could get this expression out of it. And this expression gave us exactly what the slope of that would be as a function of it accelerating in the y direction in this geometry. And in the case of the bus, these acceleration vertically was 0. It was just going horizontally. And we could calculate what that slope would be. And if we measure the slope, we could calculate what the value of this would be. And we did that. The other thing we could do also was to realize that within that fluid, we could get the gradient of pressure as you went with depth. And of course, that gradient of pressure we said was equal to minus rho plus AZ, which is this, right? Previously, we'd always thought of it as equal to just this, which of course is just equal to this term here, but, and G outside, I guess. But now if we have it accelerating upwards, then this gradient changes, so it's like going up in an elevator. If we're accelerating upwards, then the pressure increases faster with depth than it would do otherwise. And if we're dropping down the elevator shaft at gravitational acceleration, so in other words, if the gravitational acceleration was equal to, sorry, the acceleration in the z direction was equal to gravity, which is minus g, because we're going in the opposite direction, then this term would be equal to 0, and this would just be a straight line, and it would be weightless. So we talked about that last time. And the second thing was that we talked about fluids and did exactly the same thing, but said basically that if we rotate fluids around an axis, then what we expect to get is that the fluid sloshes up onto the wall of death, just like the carnival ride. And we could tell what the elevation would be as we go across it. In other words, how elevation would change as a function of radius. And it has a constant in it, and so we have to, first of all, figure out exactly where in this system we know what the elevation and the radius is to be able to determine what this term is, and then we can use it back again. So look at the other discussions last week. I won't go through it any more than this because it's not on the test, and I'm sure your interest in this might wane as a result of that. But we can calculate what the free surface would look like in these geometries. I suppose the interesting thing to look about these is that these expressions that we have here come from Newton's second law, where these are forces, this is linear accelerations, and this is a mass. And in rotation, it comes from Newton's second law in rotation, where this is an angular acceleration. So it's exactly the same expressions that are used to get each of these behaviors. And so that's relevant to what we'll do today, because what we'll talk about is accelerations of fluids which are moving with other fluids around them. So obviously in the America's Cup thing, you have the water fluid is moving, or the air is moving against the sail. Against it has other packets of air. It's not air within a container, as we talked about before, but it conforms to exactly the same rules as we had here. So what I am going to get you to think about is to think about, say, this is my idea of an airfoil, if you can believe that. And so you can imagine that you might have fluids coming around this and going downstream. We'll think that we can define kind of a new coordinate system. And each of these are streamlines. So we use this term, a streamline. And we can think about the fluids that flow around it. So this would be the trajectory of a single particle of fluid that starts off here, and then it ends up here, and then it ends up here at some later time. But we want to be able to define this behavior in a quantitative way. And we'll use Bernoulli's equation to do that. And so what we can think of is that we're interested in looking at the fluid maybe at point number 1 and maybe at point number 2. And what we'll find out that we can do is we can look at Bernoulli's equation. I'm guessing many of you will have seen it. I don't know for sure. And I'm going to kind of derive it in a second. You'll be horrified to hear. But if you've seen Bernoulli's equation, this is it. It just says that if you add together the pressure head, the elevation head, and the velocity head at 1 point upstream, then that is equal to the sum of the pressure head, elevation head, and velocity head at that point downstream. So this would be the velocity, V2 at point 2. It would be the elevation of this point relative to some datum, Z2 relative to the same datum here. And it would be whatever the pressure would be at that point as well, the pressure that we're feeling around us. And so it's important to think about along a streamline, which is S is for the streamline direction, N is for the normal to streamline direction. And we're going to look at Bernoulli's equation in these two modes. We'd like to be able to figure what this is, because this would allow us to say, if, for instance, we know what the pressure, elevation, and velocity are here, then if we know two of those terms down here, we can solve for the other one. And that's useful for us. It turns out also that if we only know one of these terms downstream, then we can use something called continuity, the same, which means that there's no volume change in the system, to also be able to determine what the other two quantities are the downstream. The other thing that we'd like to do is we'd like to be able to go from point 1 to point 3. And if we go from point 1 to point 3, you can imagine from what we've talked about before, we can imagine that there's a change in pressure as we go from these, because if we go within a fluid in a static swimming pool, from the surface down to the bottom of the pool, we know that the pressure at the bottom will be higher. And so we can think of this little trapezoid or this triangular distribution of fluid pressures. And so the other thing we might like to do is to do exactly what we've done here and write the conditions at point number 1 and point number 2 to be able to determine what an unknown value is at 2, say. What we'd like to do up here is we'd like to write Bernoulli's equation across the streamline for point 1 and equate it to the value at point 3 and solve for one of these three variables. And the three variables would be elevation or pressure or velocity at each of these locations. So that's our goal today. And so that's what we're going to attempt to do. And so we'll try and think about that. I guess the other thing perhaps to mention is to go back to this and to realize that we're using Newton's law for each of these. And so this bears some resemblance to what we've talked about before. So if we were thinking about having a packet of fluid here, let me use a different color, fuchsia. So imagine that around this point here I had a packet of fluid, and I'm pressing the wrong thing, of course, and I wanted to drag it in this direction by providing a force. Then it would be as if I had a can of water on the end of a string and I was pulling it up. I was using the string to pull it, and this is kind of going horizontally, but let's ignore that for now. That would be exactly what this is. The corollary of that for normal to a streamline is that you could imagine, let me get rid of this idea here. You could imagine me standing here and having a can of water here on a string, and me flinging that can of water around my head. I don't bring a thing with me, but imagine that I was swinging it around my head like this, and that would be exactly the same as we talked about for the relationships that we developed for this geometry here, where we were looking at rotational behavior. And so that's what we'll essentially do, is we'll take the expressions that we have so far, we won't rederive them, and today we'll do it for along the streamline, and tomorrow we'll do it, Friday we'll do it across the streamline, but we'll derive the expressions for Bernoulli just very straightforwardly. So that's our task for today. Okay? So that's my plan. So I'm going to take a coordinate system, which is this. I'm going to draw a bucket at the bottom. Doesn't have to be on that line. That line is just my divider. This is point number 1. I'm going to assume that it translates to point number 2. And actually, before we do that, perhaps it's worth me mentioning that there are 3 requirements for using Bernoulli equation. One is that it should be inviscid. The viscosity should be 0. We use it for real fluids, which aren't 0, and it works just fine in most cases. It should be incompressible. Which says that it shouldn't be a compressible fluid like a gas, like air, but we do use it for airfoils on planes, and it works just fine. So I guess the question is always, how incompressible is incompressible? So incompressible would be, we use the term beta for compressibility, so that's 0. It should be irrotational. So in other words, it shouldn't be getting little eddies developing in the flow, vortices that develop. And it should be steady state. So steady state means that if you take a picture of the flow around this airfoil at second 1 and at second 10, it looks exactly the same. Clearly, the particle of fluid that was at this point at second 1 is not here at second 10, it's gone somewhere else, but the overall flow system looks exactly the same. So it's not changing in time, so it's a static system. So even though the locations of the particles are accelerating through the system, in the reference frame that you choose, which is a static reference frame in this case to look at it, then it's static. Of course, if you're looking at airflow around a car, you'd attach the reference frame to the car and you'd be moving with the car so that the airflow around you, if you took a picture from the hood of the car at 1 second and 10 seconds, that would look the same. And so that's what we mean. Those are the 4 requirements that we need for this. So this is going to be our elevation. So for a long streamline, so static. So our static equations are dp dz, I'm going to write it in the minus direction, minus density times g minus density times az is equal to 0. This is the expressions that we started with last time that we'd already derived. This is usually on the right-hand side. I've just subtracted it off and made it equal to 0. We can think of this as being equal to, if I change this, f minus ma equals 0. Everything on the left side of this is an equivalent force. And what we'd like to do is be able to convert this into Bernoulli equation. So I don't care that you're able to do this, but I just think it's instructive to see where it comes from. And the fact that F equals ma means that we're just conserving momentum. Momentum is mass times acceleration. Acceleration is rate of change of velocity. So we could write this term ma as being equal to mass times dv dt, which is equal to d dt of mv, right? So it's a rate of change of momentum. So how quickly we change momentum is how much force we have to put into the system, or how much force we have to resist. You know, you take a fire hose in the chest, that water is hitting you, it's expending its momentum in your body. And so what are we going to do here? We're going to take the acceleration due in the z direction. We're going to write it as equal to change in velocity with time. We're going to write it as equal to change in velocity with time multiplied by, I'm not doing a very good job of changing colors here, multiplied by dz, not dt. Change in location with time is equal to velocity. So this is equal to velocity times dv dz. And so this is a velocity. This is kind of an acceleration. It's how velocity is changing, not in time, but in space. So as you go from upstream to downstream, if it's changing velocity, then this is what we call a convective acceleration. Doesn't really matter what the term is. It means that it's an acceleration in space rather than in time. And we can write this as a half d dz v squared. I'll let you prove that to yourself if you want, but that's a standard result. And so what we can do is we can substitute that back in here. And of course then that becomes minus dp dz minus rho g minus rho a half rate of change with the z direction of v squared. And then we can do some things. We could multiply everything by dz. This, of course, is still equal to 0. If we do that, then this turns out to be 1. This turns out to be, let's not worry about that for now. We can integrate it. And if we do that, we end up with p minus integral of v squared is equal to 2v multiplied, I guess, no, we don't want to do that. No, yeah, so we get rid of this, and this just ends up being density times a half v squared. And since we've integrated it and not put limits on it, this is equal to a constant. And so I guess we could gather terms. Blue would look better on this. Let's divide through by rho g. Let's divide through by rho g. Let's divide through by rho g. And then the form in which I always write this is equal to, the final form of this is pressure head. And we could put these equal to positive because we can do that, and it just changes the form of the constant. And this is equal to z plus v squared over 2g equals constant. That's it. So that's where Bernoulli straightforwardly comes from our equations of statics. The zero goes to being a constant because it's a constant of integration. And of course that means that if we want to, we can write it at point 1, as we have done, and we can equate it to that same behavior as equal to point 2. And since it's constant, then so long as we know 5 of these parameters, we can solve for the remaining one. And that's all it is. And again, still, it conforms to the fact that this, if we look at it, everything to the right side of this is MA. Everything to the left side of this is F. And when we talk about angular acceleration, normal to the streamline, then we'll use just the angular acceleration. It'll be exactly the same expression. So that's it. So that's all we're working with. So instead of doing a long derivation here, blah-de-blah-de-blah, we've avoided this. That's good. Pretty straightforward. I guess I've got smarter with time to think about what this is and to be able to define this. I always write it in the form that is shown here. That's just my favorite way of writing it. The units of this have to be in units of length. So the pressure divided by unit weight is length. Velocity squared over 2g is units of length as well. You can also write it in units of pressure if you want. It's exactly the same expression, of course. You can just do everything you want with it. And a physical meaning of it, I suppose, is given by this figure. And so this figure is looking at a river that's flowing. And you can think of the fact that the sum of these terms adds up to a constant. If they're all written as lengths, then if you take a datum, which is where you just arbitrarily write the elevation as equal to 0, and you take a particular point in that flow, then at that particular point it would have a velocity v1, p1, and z1. And so z1 would be this elevation of the point. The pressure head acting at that point would be P1 divided by the unit weight, and it would be equal to this length here. And the velocity squared head term, this one here, would be equal to this elevation. And so you don't necessarily know what this pressure, well, actually you probably do know what this pressure is. If you drew this out, it turns out you probably don't know this yet. But if you looked at the pressure distribution at this point, it would look something like this. Just because the fluid is moving at some velocity below a free surface, it's still equal to, this curve here is still equal to dp dz is equal to minus unit weight. So it's still this linear form. But this gap up here is the velocity head because it's moving at some rate. So what you could do is you could put in a pitot tube. So you take a little tube that's pointing upstream. It's actually the same way that aircraft still use to be able to see what their air velocity is. If you look on the plane as you get onto a small commuter plane, you'll see this little right-angled thing jutting out of the side of the cockpit. And it is exactly this. It points in the direction that you fly, which is usually forwards. It means that there's a stagnation point at this point here, which means that the air velocity is killed by the stagnant fluid that's inside this tube. And so at this point here, the velocity, V2, is equal to 0. The elevation of this point is equal to Z2. And the pressure at this point is equal to P2 as well. And so now, if you looked at the pressure distribution at this point is its elevation, which is what it was before. Z2 is still equal to Z1 in this particular case. But the velocity, by definition, is equal to 0. And so if this is equal to 0, then this velocity term has to be 0. And what we'd find out is that the pressure distribution to get to that point is exactly the same gradient as this, is equal to minus the unit weight of the fluid, I guess water in this particular case. And I won't draw all the bars. And it means that you're able to measure the pressure. So the idea is of a pitot tube, it has a point here, and it measures the pressure at this point inside it. It has a second concentric tube where it actually measures what P1 is on the side of it. And from knowing the magnitudes of P1 and P2, it can calculate exactly what this term here is. Velocity. That's how it works. Yeah.
Why were we able to say that V2 is equal to 0?
Because if you blow this up, this is your tube. This is the wall of your tube. This is a blow up of your tube. So this is the front part of the tube. This in it has stagnant air. So the air is hitting this. It's closed. It goes up here and it goes up here, which is this portion here. This is closed and capped off with a pressure transducer. So there is no flow in here. It's stagnant. So I didn't finish the word, but that is stagnant. So it has to come here. The velocity here has to go to 0, and it will physically go around it. Okay? And this is what we call a stagnation point. If you draw the streamlines for this point, the streamlines individually will part, like the parting of the Red Sea, around this. This will be the flow field. And of course, the port that I was talking about, it measures the pressure in this point here, and this pressure here will actually be the true pressure at this point because it's still going at velocity V1, right? This is still V1. Yeah, good question. That's it. And of course, we'll talk about in class, there's a classic example of this. It's Air France flight, whatever. 5 years ago, 10 years ago, from Rio to Paris. Went through a big thunderstorm off the Amazon coast. The pitot tube froze and therefore was sealed and couldn't tell you accurately what the air velocity was. And the plane went up and down because it was getting wrong signals to the remote pilot and ultimately never arrived in Paris. Everyone was lost. And so now they have heaters in these things so that when you go through thunderstorms and it's minus 60 outside and also wet and it will freeze ice on it and seal this, it's able to melt. And so contrary to popular belief, for fine tuning of velocities, it's measured directly, not from GPS, although it's obviously measured by GPS as well. Okay? So a couple of examples. This probably is still in the book. This is from a previous example. Again, the same kinds of ideas. If we look at these three components of elevation head, pressure head, and velocity head, for this simple example. And they do it in the book. And here's the little table at the bottom. Think about what these individual components would be at each of these individual points. And I'll just write high, low, and intermediate. So what do you think here? You have a plunger, it's in a syringe. Many of us have, hopefully all of us have been vaccinated. So you know that you need a pressure in here to be able to push the fluid in. And so I suppose at point number 1, you'd think that the pressure is high. The elevation compared to other elevations would be low. And this plunger is moving, it's not moving at 0 speed, it's moving at some speed because it's pushing fluid out. And so the velocity would be perhaps intermediate. So this would be low, and this would be kind of neutral, right? What's happening here? It's squeezing out of the nozzle, not going in your arm. What's the pressure that's acting as it comes out on the side? Has to be atmospheric pressure. What do we know about pressure at a point? Well, we know that it acts uniformly in all directions. So if the pressure acting horizontally is atmospheric, 0, it has to be the pressure acting everywhere. So the pressure here has to be low. The elevation, well, it's higher than 0.1, so I guess it's maybe intermediate. And since it's squeezing out of a small orifice, by volume, if it's moving this amount of fluid in a given time that the plunger moves forward, this amount of fluid has to squeeze through a much smaller gap here. And so you'd think that this would be large. Did I write that? I don't know. No, this is 0, right? This is low. Oh, yeah. What am I using? I'm using H, not large, I'm using high. Sorry. So, arrows are easier for me. And then you can write Bernoulli at each of these points, obviously, because this is all on a single streamline. Single streamline goes up through all of these. S. And so what happens here? It has the highest potential energy it has. It has 0 velocity because it's got to its apex. It's just about to fall. And this would be low, actually 0. And the pressure would be the same as it was here. It would be the same as this. Be kind of a low pressure. And so we can think of things in those terms. Very simple example. And you can, I'm sure this example still exists in the book. It's quite a nice illustration just to think of it. So everything that we have here is on a streamline, and so we can think about those behaviors. Let's do one final example. I won't show you the movie again. If you got late, well, it's a good reason to get here early. Let's do San Francisco International. So, see how good a drafts person I am. Got a jet engine, V1, P1, C1. Got our F-150 vintage model. We've got V2, P2, Z2. Didn't draw this very well. Actually, that's good enough. It doesn't have to be the 0. And so we've got C1. We've got, let's call it the same one, C2. And I'm going to write Bernoulli out. So it's elevation 1, pressure 1, velocity head 1 is equal to the same at the second location. Oh. Plus v squared 2 over 2g. And figure out exactly what we know. Elevation 1 and elevation 2 are the same. So this is my way of equating them. Get rid of them. Same arguments we had last time. The pressure acting at this point is atmospheric. And so the pressure, even despite you'd think that of a thrust, the pressure here has to be 0. And what happens here? This is all atmospheric as well, but if we drew the streamlines that I just kind of drew, this would be a stagnation point, which would be going around it like this, and perhaps underneath it like this. And so this would be a stagnation point. So V2 is equal to 0, which means that P2 is not equal to 0, exactly for the question that was asked. And so we have an expression where we'd like to be able to, so this term here is 0. And so if we want to write it out, I guess we have an expression that is P2 over gamma is equal to V1 squared over 2g. We could multiply both sides by rho g and rho g. That gets rid of these terms. Unit weight is this. And so we have exactly what we want, which is the pressure at point 2 is equal to density, gravity, velocity 1 squared over 2g. And that allows us to be able to calculate everything we need. So what we might want to do is we might want to draw a free body diagram. And that free body diagram would have a pressure acting. And I suppose we could write that pressure as a resultant force. And that resultant force is equal to the pressure times the area, right? And we could solve for this. Got 5 minutes to do it. So let's take some numbers for this. I think that the weight of the mass of an F-150 is equal to about 1,500 kilograms. So the weight is equal to the mass times gravitational acceleration, which is 10 meters a second squared, which is 15,000 newtons. Density of air is roughly 1 kilogram per cubic meter. Gravity is, so this is 1. I'm going to use the velocity is equal to 100 meters a second. It's a ratio of 1 to 2. So that velocity is also equal to about 200 miles an hour. So I don't know, planes fly at 600 miles an hour, 500 miles an hour, 0.8 of the speed of sound. Takeoff speeds are 120 miles an hour, something like that. So this isn't unreasonable if we use that. And we have everything else we need. And so we could calculate the pressure if we want. And the pressure is going to be equal to 1 times 10 times 10 to the 3 squared over 2 times 10. I guess actually we can make our life easier. by not even doing that, which should be equal to half times 10 to the 6. It's going to be in newtons per meter squared, even though I haven't pulled the units in there. And then we're going to draw a free body diagram to see if that's enough to be able to push it over. So we have a magnitude of pressure. So we could take this geometry now, and let's look at this geometry. Shout the questions if you have them. I can almost walk and chew gum.
I do have a question.
Yeah.
Before, we're solving for pressure there.
Yeah.
Why did we use 10 to the third for velocity?
Because I'm just choosing it for the velocity, 100 meters a second.
Okay. Would that be 10 squared?
Yes, you're right. Thank you. Great question. That's right. Ask them questions. And this is equal to P. And P is equal to pressure times area. So we can write a little relationship here that I'm going to use this LP and LW. A truck is 6 foot wide, right? So this is 1 meter. The truck, close to, is about 1 meter to half height as well, right? So if we resolve moments around this, then pressure times area times LP is equal to the weight times LW. I'm going to make each one of these, I guess I could do this, right? Bless you, again. These both cancel out at 1 meter. And I guess then this would be equal to the weight of the truck that would just be blown over is going to be equal to the pressure times the area of the truck. And I think the area of the truck along here, I could imagine it as being 3 square yards, right? 10 feet long and 3 feet high. This would be 3 meters squared. And so 0.5 times 3 meters squared times 10 to the 4 newtons per meter squared should be equal to 1.5 10 to the 4 newtons, which is equal to 15 times 10 to the 3 newtons, which is equal to 15,000 newtons, which is equal to 1,500 kilograms. I don't often get things right. Well, I didn't completely get them right. I was off by a factor of 1 on the velocity. But that's, so in other words, this is saying that if your truck is 1,500 kilograms, then it will just be blown over. If it's 2,000, then it wouldn't. If it's 1,000, then it would. And so it's just an order of magnitude estimate to see what's going on. So that's it. So the bottom line is that we'll use Bernoulli. It comes exactly from force equals mass times acceleration. It's conservation of momentum. We wrote F equals ma in a slightly different way, as equal to the rate with time of change of momentum, because this acceleration term is rate of change of velocity with time. It's how quickly it's turning the velocity, the momentum of the air that's coming out of the plane. It's killing it, completely killing the momentum, turning it from some big number to 0 as it hits the truck. And that transfer of momentum is the motive force, uppercase P, which is applied to to move it. And so we can get those forces, and if we can supply a free body diagram that kind of shows what the failure mode is, in other words, rotating around the base of its far away from the engine tire and going over into the San Francisco Bay, then that allows us to be able to say exactly what the weight of the truck has to be and the mass of the truck has to be to resist it. So that's it. So next time we'll talk about the corollary of this, and that is for spinning a weight of fluid in a bucket around my head, and we'll introduce it with the idea of water going through maybe one of these fairground water slide things where you come down the slide and it loops the loop, because it's as if it's going through a vertical circle, right? If I was spinning a can around my head, why does it stay in place and not just drop down? And so we'll talk about flow normal to a streamline to be able to explain that. That's it. Right. Good seeing you.